Hello, we are Team 10, and we were working on machine learning analysis of atomic dynamics in renewable energy materials. Our purpose was to apply machine learning strategies to inelastic neutron scattering data to increase our understanding and enhance the development of materials that are essential for advancing clean energy solutions. We worked on two main sub-projects. The first one was background subtraction, where we used machine learning to remove signals in the image that did not come from the material that we analyzed. The second sub-project was forced constant inversion, which also used machine learning to extract main model parameters from the dataset.
Now for the background subtraction project. The main goal of the project is to be able to train a machine learning model to remove the background noise from neutron scattering experimental data. However, when trying to do this, we ran into many issues. First, we had to generate training data because we had a limited amount of experimental data. When trying to generate the data, we ran into many issues in itself because we had to take into account the different planes in the code. Once we were able to automate the data generation process, we were able to process the data and train 8 different models each with different amounts of data. Here you can see 2 models we trained. The top one is iron silicide and the bottom one is germanium. The last image shows the model's progress, and you can clearly see how it is able to remove the rings from the Bragg peaks. For our future steps, we hope to train more models with different materials. For example, we're currently working on training a model with both iron silicide and germanium combined. And we also hope that we can improve the model architecture.
Our second sub-project is to inversely predict the force constant using ResNet-ML model based on SQE images. Because going from force constant to SQE can be done using physics theory, but the inverse isn't that straightforward. So we used a convolutional neural network called ResNet-18 to predict the force constant using clean SQE images as training data. And we want to evaluate the model performance under noisy conditions. So we augmented the dataset by adding Gaussian noise through this defined noise function. And we varied different noise strength from 5 to 30 and feed it into the model to predict the force constants. And here are the results of the model predictions. This is the box plot for the absolute relative error of Gaussian noise. We can see that any kind of noise, regardless of the strength, will break the model easily. This shows that our model is noise resilient, so our future work will take this into account and train a model with noisy images to get better performance.
Here shows our flowchart for the MSE model training. We feed the simulated SQE images into the training model, and it predicts force constants. The loss function is defined by the mean square error between force constants. Also, we are exploring a new metric, Earthmover's distance, which could help us compare the SQE images. It is the distance function defined between probability distributions on a given metric space. And by implementing the one-dimensional Earthmover distance function into each column of the SQE image, the criterion makes great sense in physics. We have proven that the metric could be used with PyTorch in the machine learning, and we are working on the challenge of preserving gradient functions throughout the process. Here's the new flowchart for EMD training. By a second simulation process, we get a predicted SQE images, and the loss is defined by the Earthmover distance between the predict SQE and input SQE. The training is still in the process. In the future, we will further explore the potential of this loss function and optimize the training with hyperparameters. Thank you for listening.